because, it can still be infinite. Then we managed to convince him that something like scales as a log is still, it can be infinite, but it's still a small number, so we can call it a local. But he was like a true mathematician, very stickler for definitions.
Yeah, I mean, people like that have their place on some projects and not on others, right? It's kind of their role. I talked to Peter Muka a little while ago, who collaborates with Mason Porter a lot, and he says on one of the Mason's also very much a stickler, and on one of their papers they got to version 47 before Mason approved it.
Mental reminder: not only will I don't like having Mason Porter actually as one of the reviewers, because we'll come back with the review and there'll be 47 items, each numbered.
47 items.
Feels like lots of things. He is.
Yeah, no, he reads every word and thinks about every word.
But also shouldn't try to write any papers.
I know. I'm one of my papers is with him, and I submitted what I thought was a very fine paper to him, and it came back with a number of comments too. So we'll get it published one way or another.
Okay, let me go down and see who else I can round up.
Yes, it was announced. We thought it was a 6th floor, so maybe some.
Oh, okay.
So yeah.
And of course, there's refreshments. Well, no, actually not. I'll be back.
I'm Zach.
Hi.
Mama.
Nice.
Yeah, so I've never sold this in front of a computer scientist crowd. I imagine the reactions will be somewhat unexpected because every crowd has their own interests. So we'll see. We'll see how this goes.
Zach, could you lower your mic on the actual left? We might get an echo.
Sure.
Are you at your desk right now? Okay. I started the recording. Is there any way that you could just pull it up to make sure that he's audibly heard? Okay. I'll hold on. I'll stay with you. Whereabouts?
So I just turned off my microphone.
Okay.
Hopefully that's what was wanted.
We're going to do a quick audio check to make sure that
Sure.
people who are watching.
That's great. Do we usually have a big remote audience for these things?
On a Monday, it can be tough to get a lot of people.
Well, no, I mean a remote, because we're recording this and.
Usually too many. Right. Usually, if someone's out of town on a meeting, they like to call in.
Oh, okay.
Or if they just miss it, I think, and watch it later,
Yes.
these will be referred
It'll
to.
be online.
So people who are at a conference right now or something
They can see it later.
watch it when they get back.
Is that opening up?
Yeah, I mean, I've watched only in my whole life two talks that I wasn't actually physically present for. I don't know why. There's just something about the setup of walking down the hall to a meeting that makes me much, much more likely to participate.
I mean, it's nice to have, when the recording's public, it's really good, like on video lectures. Sometimes if I'm reading a paper that makes no sense, the actual conference talk does make sense.
There's hope, yeah.
They might give you some insight into an equation when they're presenting it, but you don't get in writing.
Well, and it is hard when you're writing because you have to defend yourself so carefully in writing. Whereas when you're talking, you're a little more free to say what you really mean. Even if it's not technically true.
Reviewers who are about to attack what you wrote when you're at a conference, usually people are a little friendlier. they can see you, they don't want to make you cry. Whereas the reviewers...
Good to know there's still a heart in computer science. Mathematicians, it's kind of too much. They're kind of too nice. As long as it's technically correct, they won't say anything.
All right, we got. I think everybody else, I think, is sleeping in.
It's okay. I would never begrudge people their sleep.
Of course, it's good for mental health. All right, so let's give it one more minute.
Sure thing.
Even though recording has started.
I think we're still doing a sound test too. Oh.
Yeah, I think we're okay.
Yeah.
Okay.
Just wanted to double check on it.
Yeah, we have a transition to a new technology using Skype or whatever, Blue Jeans, stuff.
I've never used Blue Jeans.
We had a fancier system, much fancier, but it was too fragile to use.
Yeah, I mean, it's still surprising to me how unsuccessful overall video conferencing technology is. I mean, just the number of things that can go wrong and ruin your meeting.
That's why
many.
there's so many new companies that are starting on Zoom meeting, GoToMeeting, like there's so many different.
Zoom has been pretty good to me.
All right, well, I'm looking at 11 though. Oh, we can.
And you can have what's called.
Okay, thanks. Thanks, Peter.
Yeah.
All right. We are a small but dedicated crowd today. Going to, I would like to all of you join me in welcoming Zach Boyd here. Zach is interviewing for a postdoctoral position here at one of our couple of our projects, let's say. So Zach's background is actually mathematics, a little bit unusual for the kind of seminar speakers we have coming in, but as you'll hear, it's quite appropriate to the kind of work we're doing here, because he's taking a mathematician's view of problems in network analysis, such as community finding, and Zach is going to tell us about how he actually mapped the community detection problem to a well-known problem in mathematical geometry. And, so please join me in welcoming Zach.
Thank you.
At some point, like 45 minutes and like 10-minute warning.
Okay, that'll work well. Yeah, so like Christina said, this is kind of an interesting project in the sense that all we did is take existing community detection formulations and ask the question, how would someone in math and PDE theory look at them, partial differential equation theory, and look at them, and can the tools that they've developed in that field apply? In a sense, it's kind of a promising proposition because so much work has gone into solving partial differential equations in all kinds of settings. You know, the top largest computers in the world are kind of optimized for this sort of thing. And so the hope is that if you can port the technology over, it would be useful, and you might be able to get some theoretical understanding and some guarantees that might be hard to come by from the other perspectives that people look at these problems from. And so this is really kind of a proof of concept work. I haven't taken, the Sequoia supercomputer and run this on 10 billion nodes yet and seen how well it works. But the results are promising enough at this point that I think it's worth sharing, and the theoretical insights may at least be interesting to people and lead to some further good work. Yeah, the screen wants to turn off. It will be okay. I'll of course credit great co-authors I've had. Egil Bai and Shicheng Tai are in Norway. They're GraphCut people and ADMM people who kind of had some insights into the algorithms, and then Andrea Bertozzi's the PDE expert, and Mason Porter knows the network science. So that's kind of how our team was assembled. And I now know kind of everything for this project because that's how it works. Okay, hold on, it's not changing the slides. There we go. Okay, so you guys know networks are everywhere. Every day we understand a new place where this kind of data structure comes up. From a mathematician's point of view, it's a challenging data structure because most of the problems of the previous century have some kind of regularity to them. There's a continuum, there's the symmetries of the continuum, we have vector space structure and things like that. But on a graph, one of the hardest questions is what kind of regularity and what kind of patterns are present and how should we think about them? Where's the structure and where is the noise? And also, I don't need to tell you guys about the applications. You know tons about how to do networks, probably more than me, actually. But the one thing I want to highlight is just how I see kind of the march of the community detection literature over the years. And it's still evolving as far as I'm concerned. But we've kind of gone from very simple ideas like, well, for a community to exist, there should be more inlinks than outlinks to more statistically based ideas like maximum likelihood estimation off of generative models, and then the endless elaborations you can do through Bayesian methods and marginal likelihood estimation and careful guards against overfitting. And then there are other methods that are just totally off the wall, like the minimum description length principles or conductance-based methods, dynamical methods like WalkTraps, and then other further elaborations like overlapping communities, time-dependent communities, multiplex, and so forth, local methods. For the sake of a proof of concept work, we're just going to focus on the simplest ideas of undirected, simple graphs. The question of how well this generalizes is interesting, but it would change the corresponding paper from 20 pages to 75, and we don't want to do that. And so out of all the perspectives on community detection, I think what I'm going to present is most similar to how the statistical mechanics people have viewed communities, in the sense of just taking networks, saying, oh, this is kind of like the thing that we always work on, and showing that their techniques apply. So I think the analogy is very strong there. Computationally, community structure is really hard. Not only is it provably NP hard, you can look at the energy landscape, and it's horrendous. The paper Good et al. Did some heuristic explorations where you can see the energy landscape is it's really easy to eliminate some poor possibilities immediately, but then you get super exponentially many local minima that are not close to each other in the state space. So in other words, you can tell when you have a bad community fit sometimes, but if you can't tell which one is the right one, because it's so hard to navigate. Go ahead.
According to which definition of a community?
That's the question. So the Good et al. Papers in modularity, right? If you go into something like stochastic block models, then it depends, because there's the detectability transition where there is a right answer for a while and there's not, and so forth. But the Good et al. Paper is in modularity. And then just from an embedding theory, networks are high dimensional objects. They're not spatial most of the time. So everything is hard about this problem. And my view of kind of the state of the art, which you guys may be able to comment on if there's some things you think are not quite right, but we've done a lot of testing on some examples where we know the answer, and we can replicate what we think we know the answer is, and we can compute on networks with various things like metadata, time dependence, and so forth. But it's still very challenging to tell if we've got the right answer, and determining what the appropriate model is we should be solving for, and determining what's going to trick our methods. So now I'll just go into the methods that I worked on, which to me are kind of the most popular ones, despite criticisms about them, which are modularity and stochastic block models. And the short story is that modularity optimization I viewed as a total variation minimization problem, which has a geometric interpretation that we can talk about. And then the stochastic block model, when we get to it, turns into a surface tension dynamics problem, which I think is really, really interesting to think about. But I will mention before I dive into this, there was one other paper before ours that linked modularity and total variation minimization. And the differences between the formulation I'll show you and the other one are all technical, in the sense that their formulation was more non-convex, which made the computational efforts more difficult, and the theoretical guarantees less available, and so forth. So I can go into the details of exactly why this is original relative to the other one, but I think the audience here is most interested in understanding the main idea for now. Okay, come on, there we go. Okay, so I think, can people nod their heads if they know about sparse optimization? Okay, I'm seeing mostly nods.
I don't think Indian nod.
What? The anti-nod?
No, Indian nod.
Yeah. Oh no. Yeah, I forget we're multinational here. I'm going to assume we've mostly seen compressed sensing and things like that before. And I think this is relevant because some of the most popular community detection methods in network science are basically spectral methods based on a Laplacian, which ultimately is an L2 optimization method. And you can get these wonderful solvers in the spectral methods that will automatically advancing sometimes, which it shouldn't do. But it's you can get these wonderful solvers that will find the eigenvalues with high accuracy and good efficiency. And then when you need to threshold back to something discrete, you kind of lose. You have limited theoretical control. There's Cheeger's inequality, which gives you some bound, but it's not clear how well you recover the right answer. So what I'm going to present is kind of the L1 version of this, that kind of natively is going to promote something that is sparse, which gives you classification information instead of this continuum relatedness information. And so the inspiration for this is total variation, which I've been exposed to in image processing context. The common scenario there is you've got some kind of an instrument that can take a picture, maybe a nano picture or an astronomical picture, but because of the measurement setting, whatever you're going to get back is corrupted by noise. In this case, on the middle picture, you can see there's some salt and pepper noise, or I don't know, some kind of noise has been I'm sorry. There we go. Has been superimposed on the picture, and the goal is to recover the original. And so in this case, you don't want the picture to be sparse, but you want the derivatives of the picture to be sparse, because suddenly the color intensity will change from 0, that's white, up to black. And so you want the derivative to be sparse, so you regularize, you fit to the observed image with a regularization on the total variation, which is the integral of the absolute value of the derivative. And this behaves exactly how you would expect if you have seen the sparse optimization methods. If you use the one on the left, total variation, you get what you expect. You get sudden jumps in the intensity like some pictures are supposed to exhibit. And if you use the one on the right where you square the derivative, you're essentially doing an L2 minimization technique, and it will blur the edges. And this is super well known in the image processing context. It keeps changing the slides on me. I'm so sorry about that. But so we're going to do total variation on a graph. And the idea is going to be that you want some indicator of belonging to a cluster. And you want, as you move across the graph, you want to jump from 0 straight up to 1. So you have a clear boundary for where you want your cluster to be. So some standard notation, we've got an adjacency matrix. As I said, this is a simple unweighted, undirected graph. We've done it with weighted graphs, but not really with anything fancier than that at this point. You compute the degrees k of each node. M is the number of edges in the matrix, or in the graph. And we're going to use G to identify a partition of the nodes of the graph. So it's a map from the node indices to the community indices. We're not going to assume that G is a good partition of the graph. The goal is to find a good G. So as you guys are probably aware, we've got modularity here that originally was, so the sum here, to be clear, is summing over all pairs of nodes I and j such that their assignment is the same in the proposed clustering. And this has the intuitive idea that you're taking, for any two nodes that are placed in the same cluster, you're taking the difference between the observed weight of the edge between them and the expected weight of the edge between them in some kind of a null model. In this case, a configuration model. And the idea is that high modularity partitions may represent a significant departure from randomness, and thus have something to do with the generative structure of the graph. This has been criticized in various ways, but the fact is that modularity is still very, very widely used, and is kind of the first choice for many people when they're out. Okay, so we don't need to go through all of the math here, but we're going to reformulate modularity in terms of something that looks more like total variation. Shoot, I don't know why it's changing on me. I'm sorry about that. The main trick that you need to be aware of is we're changing a maximization problem to a minimization problem with the trick in the first box, where you take, instead of the sum over all nodes that are in the same community, you sum over all nodes that are in different communities. And the fact that there's a constant number of edges makes this an easy switch to make. And then in the bottom, it's just algebra, and you get that. But so the modularity, if you do this change, is a minimization problem where you sum over the graph cuts of each community, or supposed community, plus a sum of the volumes squared. In the version of modularity I presented here, you sum the degrees of each node. In the non-degree corrected form, you just sum the number of nodes. You take the number of nodes. Go ahead.
So the volume squared is just to make sure that they're similar sizes constraint. I mean, that wasn't part of the original modularity, the volume.
It wasn't intended to be in there, but it is in there. Like this is exactly equivalent to what's on the previous slide. Yes, this is exactly equivalent to what's on the previous slide. Assuming
so volume is just number of edges.
Yes, it's the number of edge stubs. Yeah.
Within the
half edges. Yeah. Yeah, and then you square that, and this wasn't intended in the original modularity formulation, but this formulation shows that
once you make the transformation.
Yeah, exactly. And what the volume terms are small when the volumes of each community are roughly equal. And so it's a balancing term.
Balancing, that's what I meant.
And so this is kind of the source of the resolution limit in modularity from a geometric perspective, is that there's this, and if you could say just remove the volume terms, but then you get nothing because the sum of the graph cuts is always going to be constant. Well, and it's hard to think of what to replace it with that wouldn't have a resolution limit. But that's ultimately what's going on. for the volume terms. And so now the next thing I need to do is convince you that the graph cut is a geometric object of interest. And the basic idea here is that if you took a shape in 2D, so you're in the plane, you have a shape, and you want to compute the area, or the what do you call it, the length of the boundary of the shape, or if you're in 3D, the surface area. Well, if you just take a fairly discrete, a fairly fine-grained discretization of the space and put a grid on it, the most reasonable approximation of the surface area is just to count the number of edges that cross the boundary, and that's exactly the graph cut. And so this is kind of the key informal insight that lets you port all of the geometric PDE technology over, is you just blindly accept that, well, not quite blindly, but you accept that the graph cut will have some geometric meaning, similar to the meaning it has when you're on a regular. And we don't have a theorem that says that will work, but you'll see in practice that it does on the ones that we've tested. It would be nice to prove that this will work. So anyway, so we've got something that's kind of formulated in a way that's familiar to people who have worked in geometric PDE theory. And so now we're gonna do geometric PDE. So we have the total variation definition on the continuum space. On a graph, we'll use the definition that's listed down there, where U is any function on the nodes of the graph. So the nodes now correspond to points in space. And so instead of an integral, you have a sum. And instead of a derivative, you have a finite difference. Where if you imagine A to be weighted, you think of Aij as an inverse distance, basically. If nodes are very similar, they'll have a high weight, which means you're essentially dividing by a line. And actually, this is not our invention for a definition of total variation. There's a very interesting literature where people have basically tried to extend as much of differential geometry to the graph setting as possible. And it's actually fairly successful. It's shocking how much transfers over. So what you can do is you can start with a measure on the space and the appropriate inner product, so you can define tangent spaces and gradients, and you can go through and you can derive the Laplacian in a principled manner. And this is the definition of anisotropic total variation that comes out of that methodology. So we didn't invent that, but we will use it. And so when you do that, the kind of natural relaxation of modularity is going to be a sum of total variation terms plus a sum of what I'm calling volume terms, which is just a weighted sum of degrees. And so whereas the previous definition was defined only for sharp partition, or for strict partitions of the space, this is defined for any set of n hat functions on the space. If they all turn out to be characteristics functions, then you have a partition of the space. Go ahead.
But this is non-overlapping communities, right? You cannot.
What I'm doing here is non-overlapping. You could conceivably extend it.
You can.
Yeah. I have not done it, so I don't know the details of how it would work. But yeah, I think in principle, there's no reason you could not do it that way. Yeah, so the idea in total variation minimization, one of the reasons it's been so successful is not only are the minimizers discrete, but when you want a discrete problem, you can minimize over the space of all solutions, discrete and smooth, and the minimizer will frequently turn out to be discrete anyway. And there are some settings where you can prove this as a theorem, but at the very least, terms like total variation are seen to promote this kind of sparsity and give you good optimization techniques, because you can solve a relaxed problem instead of a combinatorial problem and still have some success. Yeah, so that's what we're going to do. But the one thing that we're going to do first. Oh, and then I go through why you don't want to do the L2 version of this. But well, I'll just say briefly. So I just took, in the case n hat equals 2, the energy as I wrote it on the left, and the energy on the right as kind of the L2 version of that, just to point out that this is kind of the L1 version of the spectral methods that are done in the graph theory. Although the energy on the right is not exactly what they solve for in the spectral methods, but it's closely related. We can't. One of the hopes that we had was that the total variation case would be, like I said, where you can just solve the relaxed problem and get the answer right away. And it turns out we were surprisingly able to prove the opposite, in the sense that if you just take the totally naive relaxation and solve over the full function space, that you will be guaranteed to get the wrong answer, in the sense that the global minimizer of this is going to be the constant functions, which makes sense because constant functions have no total variation. They're constant. So, and you can prove this with a mixing argument that I don't think we need to go into, but I'd be happy to explain it later. But just even if you were clever and thought of another convex relaxation, it wouldn't work. Any convex relaxation of modularity in a space like the one I'm describing will fail. So then the next thing I'm going to show you is how to do a non-convex relaxation of this using methods that are familiar to math people. Anyway, so let's skip the gradient descent or the gradient descent stuff. But this yields mean curvature flow, and we tried it on a different problem. I'll explain that in a minute. But given that you can't do a convex relaxation, we came up with a non-convex relaxation. I wonder if there's just a lag between the screens. Anyways, this is our non-convex relaxation. And it's well known in certain math circles, where you can take the total variation term and relax it by replacing it with an L2 term. So you do square the gradient, but then you have to add a potential there. And that's the 1 over epsilon t of u term. And the potential just actively encourages the discrete states that you want. So in the case of only 2 communities, it would be basically a quartic function that has a minimum at 0 and 1. And so it just has to actively encourage things to fall into the correct wells. And then you can prove both in the continuum and in the graph setting that as your epsilon parameter goes to 0, the minimizers of these 2 problems will coincide. At least given some technical details that are fairly real. But the nice thing about this is that you have a smooth leading term, and you can just do gradient descent of this. And this has a name. It's called the Allen-Kahn equation in the continuum. On a graph, it's a little different. And we won't go through the definition of gamma convergence, but it makes the minimizers coincide when you send the approximation parameter to 0. But the Allen-Kahn equation's been well studied. We know how to build good solvers for those. In fact, even in the graph case, a recent paper has showed how to set the time step so that it's guaranteed to be monotonic. We know how to solve. This actually ends up being a stiff dynamics, which means there's multiple time scales to worry about, and we know how to work around that, and it works great. The other thing that you can do with this, besides just do the direct gradient descent, is threshold dynamics, where if we go back to the previous slide, which it is definitely going to do now. Okay, you go back to the previous slide. If that epsilon parameter is small enough, what it does is it essentially just always forces the solution to fall into the nearest discrete point. So if you did just a time step solver where you first do the diffusion for the graph Laplacian, and then you apply the t operator, and then you apply the last operator. The point where you apply the t operator that thresholds it down to the nearest potential well is essentially just going to be a thresholding, and so you don't have to do the dynamics, which would be cubic, which would involve cubic terms and be a little harder to handle. So you can actually just do a very simple thing, which is get rid of the well potential. Just do alternated diffusion and thresholding, and it will work. It's a good approximation of the other method. And also there are papers showing the appropriate time step bounds, and so we have good theory for how to implement this and when it should work. And just our applications at this point have been very simple because we're just doing modularity optimization. We're not doing a new graph clustering heuristic. It's an existing one. We know when it fails and when it doesn't. So the real work is just to show that this will successfully solve the problem that we wanted to solve. So you can do some standard things like build a synthetic social network, and it will get the correct community structure. This particular model has communities of different sizes and connectivities, and it tends to be somewhat realistic. The target application that actually probably officially funded this for Andrea was hyperspectral imaging, where you can. So a hyperspectral image is a little different from a regular image. A regular image has a red channel, a green channel, and a blue channel. Hyperspectral image may have hundreds of channels. And the idea is you can take these kinds of images from, say, a satellite and get so much information about the object you're taking a picture of that you can just identify the composition of it from. Basically, you can understand some things about the chemistry, and so it's applied, but it's a hard problem. What they want to do is basically take a picture and segment it and identify what's in it. But it's a hard problem because for a human, you can't look at it and figure out what's there because all the channels only contain a small part of the information that you need to figure out the composition. So the kind of application or the way that we did this on a grant was to take each pixel of the hyperspectral image, take the long vector of data associated with that pixel, and also take a neighborhood patch, incorporate some of the neighboring data. So at the end, you end up with a very, very long vector, with a few thousand components or something. And you just build a similarity graph out of those vectors. And then you can just do graph clustering on it. You can do graph community detection on it, and it works great. We compared it to this one. We've compared fairly extensively again because it was kind of on a grant and we were on the hook for it. But our method, it detected the invisible gas plume on the left beautifully. This is kind of a hard one because the boundary is very disperse, and it's not clear that there is a good cutoff. But spectral clustering did not work as well. NLTV is out of Stan Osher's group, which is absolutely one of the best in this field, and I think we got the plume sharper than him because the trailing edge there was not present in ours. And then Gen Louvain is just a standard modularity solver that implements the Louvain technique. And Gen Louvain actually did something very reasonable by splitting the plume in half. Where it splits it is where the horizon is. And so it really is seeing something different there when the light goes through the plume and hits dirt versus hits the sky, basically. So it did something reasonable, but it's not actually appropriate for this particular application. It turns out the modularity of its solution is just ever so slightly better than ours too. But go ahead.
How did you said it's not really, humans cannot look at the image, humans cannot tell where the plume is?
Not really. I mean, you can get a faint idea.
So how do you know that you're doing better than Stan Osher's approach?
Okay, well that's a really good question. Okay, so you can see the right idea. I guess probably the real answer is that domain people think that there's not gas over there. But you're right. I mean, there's this verification question. As an optimizer, you should really just look at the modularity value and decide what's better. But applications people want it to actually match to replicate their intuition in kind of a reasonable way. And I think basically the application people have decided that there is a column of gas there. Good question.
So
Go ahead.
follow up. So if you say that the rule of thumb that you could take is that you pick the highest modularity values, then why not picking the Louvain that you say has a slightly higher modularity value than your solution?
I thought a lot about this because it was confusing to me at first. And I think there are a couple of good answers to that question. The first answer is that the domain people want something that matches their intuition, and so I think to a certain degree this is a manifestation of the model misspecification of modularity, where the energy landscape's just bad, and there are things that are dissimilar that are scored similar. And in this application, that's not good. So it would be better to have. I mean, one thing we could do with this method that in this particular domain is probably useful is do some semi-supervision and just kind of give it a nudge toward the right part of the energy landscape. But yeah, I mean, I think the real problem in this case is that there's a small model misspecification in modularity that makes it so that it identifies the wrong thing as equivalent or slightly better. On the other hand, it's not totally wrong because a human could successfully say that that's different from the ground, even though the Gen Louvain thinks that it's two things instead of. Anyway, yeah, it's kind of a hairy issue, and I think the real answer lies with modularity not being totally the right thing for this problem. Although it's close, I mean, it gives you reasonable result. I mean, the fact that this is totally unsupervised does matter. With a small amount of supervision, you get much better result. Okay, so now we'll go to the second application, which is stochastic block modeling. And I'll start by talking about the physics problem that we identified this with, which is crystal grain growth. This was like very hot in the 90s. It has big applications in metallurgy. And the idea is that metals can be roughly modeled as being composed of a bunch of small crystals that are stuck together, not necessarily aligned with each other, which is why they aren't bonded into the same crystal. And as part of, and the structure of these crystals determines the properties of the metal that you're working with to a certain extent. And so as part of metalworking, they'll do annealing processes that allow the many small crystals to grow and gobble each other up. And at the end of this process, you'll have a smaller number of crystals with a lower energy configuration, and this alters the strength of the metal and other things that matter in the application. I'll show you a video of how this works. And it's going at about the right. So there, it started with a bunch of crystals, and now you can see them kind of merging together. And the motion on each boundary is motion by mean curvature. That's why it's always approximately linear, because that's what it wants to be. It wants to be flat. And then at the junctions between two or more phases, there are different rules that it follows. And actually, the rules at two or more phases are not well understood on a theoretical level. But the energy of this system can be caricatured as the weighted sum of the surface areas between each of the crystals. And the weights are determined pairwise by each pair of crystals because of physics details that, frankly, I don't understand very well. But it has something to do with how the crystals are not all aligned the same way with respect to each other. The lattices, that are only a little bit misaligned, have a different energy as to if they're like highly misaligned. So this is the energy that it's minimizing, and this problem's been studied to death because it's really important in applications to figure out what the properties of your metal will be after you work it, or at least what you're really doing to the metal. So this is the problem that I'm going to propose is essentially the same as stochastic block modeling, but in a continuum setting rather than on a graph. Has a little bit of trouble when I finish the video. Okay, so we talked about it follows the gradient descent of the energy that I said, locally mean curvature. Okay, we talked about it. There are really interesting PDE questions under here, but we don't have time. Stochastic block models, you guys basically know this, but to get a baseline, there are a million variations of this, but the general idea is that you start with n nodes that identify themselves as being part of n hat different groups. And based only on their group memberships, there are affinities, omega, alpha, beta, that determine how likely they are to draw edges between themselves and a member of another group. And then you start with a fully disconnected graph and just draw from a random distribution for each pair of nodes to determine if there will be an edge there. And these omega parameters control the distribution so that more or less edges appear between different groups. And then you can use this for community detection in various ways. The simplest one is maximum likelihood estimation, where you just observe a network and ask what underlying group structure and parameters omega was most likely to have generated it. So we're going to go with the simplest maximum likelihood estimation for now. I've kind of done a little bit of testing, and this is extensible to some more sophisticated models, but we'll do the simple one for now. So the likelihood of G and omega given A is essentially that thing. And then you can take log likelihood to get an objective that you want to maximize given A. And I'll point out right now that as a maximization problem, this is hard because the log term and the omega term interact. And so at all times, there's a linear scale and an exponential scale mixed. And this causes various solution methods to want to blow off to infinity. And indeed, the optimizers of this model do have some of the omegas. Well, in this scale, at 0. So you're taking the log of 0. And so there are some hard multi-scale numeric issues that will arise that I can geek out about if you ask me about them. But using tricks similar to how modularity optimization worked, you can formulate this as a graph cut problem. And in fact, modularity is known to be a special case of stochastic block modeling when you fix parameters a particular way. And so the first set of terms is what will be analogous to the stochastic or to the surface tension problem, where you take in a weighted sum of graph cuts. And here the W's are just the negative logs of the omegas. And so basically, in this context, the W's are modeling the surface tension densities between pairs of crystals. So a community will correspond to a crystal, and the W's are, in the stochastic block model, they're the affinities between those communities, and in the physics problem, they're the energy densities for contact between them. So a big W corresponds to a large penalty for edges existing between these communities. And then the volume terms at the end are not really part of the model that I just showed you, but various papers have explored the effect of including volume constraints, like, for instance, volume conservation of each crystal, which is appropriate in different contexts. So the idea of volume being a hard penalty is well known in the physics literature. Here it's kind of a soft penalty where you want the volumes to be a certain value based on the null model that underlies this. Okay, and so we talked about the optimization. Okay, so here's where I do want to talk a little bit more about mean curvature flow, which is how I said the dynamics occur in the physics setting. And Yves van Gennep and other people have come up with the appropriate notions of graph mean curvature flow, again using this differential geometry on graphs idea. And it's basically a minimizing motions technique because there's no infinitely small scale on a graph, so you can't do the continuum flow. You have to do discrete jumps in the space, and that's why you're doing an argmin construction where you go from one set to another. But you can implement this on a graph. You have to control each interface separately, so that there are some computational details to how you do it. But we found this to be very effective. It was fast. It was reliable. Despite the energy landscape being fairly tough on some of these. I'll show you a couple of the results that we got. And as before, you can approximate away the discrete constraint and do a Ginsburg-Landau approximation. The differential equations are way fancier though, because the diffusions are all coupled together in that first term when you do a gradient descent. But we can prove a convergence result that if our approximation parameter is small enough that we're solving a problem with a similar optimum. You can do the threshold dynamics as before. Again, it's more complicated because all of the dynamics are coupled through that matrix W. This problem, unlike the total variation problem, you did have to do a fair amount of fiddling to make it work. The PDE packages didn't just work right out of the box. And so, especially with the W adjusting itself and keep trying to flow off to infinity, you need to force it to adjust slowly. And it kept getting stuck in local minima where you really should be merging some communities that it accidentally separated. But once you put in a simple wrapper that checks for these things, then it works right out of the box. You just need to figure out the 2 or 3 little failure modes and check for them. It's very easy to check whether you should merge some community and so forth. Yeah, so I'll show some results. So we did 2 sets of tests. Sorry, it's jumping too far again. Okay. There we go. Okay, results on synthetic networks. So to explain, so mean curvature flow, Allen-Kahn, MBO is the threshold dynamics, and then KL is just the Kernighan-Lin simple approach where you just basically do a greedy swapping approach. And the scores here are for 3 networks. P is a planted partition model, so a very simple stochastic block model. LFR is the known test network. And MS is one that I made up basically because Mason Porter and Alex Arenas said that this would be a stretch for almost all of the solvers they knew about. And it's just a simple synthetic network. You take a densely connected network of 10 nodes, then one of 20, then one of 40, all the way up till 5,000 and something. And then you just sparsely connect each of those to their neighbors. And the idea is this has communities at very, very different scales from 10 up to 5,000. And a lot of solvers will merge the tail together or something like that. And this one did perfectly. The scores that you see are so it's the ground truth value of the objective function relative to the one recovered. So the recovered minus the ground truth divided by the absolute value of the one recovered. So 0 is perfect, negative is better than perfect, positive is worse than perfect. So it perfectly recovered the planted models, including the one that was supposed to be fairly challenging for most solvers. Unsurprisingly, the Kernighan-Lin method faced some difficulties because it's not a very sophisticated approach. The next one, we did some real networks where the results were much more interesting. So we did some Facebook networks, and then we did the Plumes example again because it was of interest to people who funded us, and the results were mixed. So remember, negative is good for here. Negative means better than the reference partition. Because we don't know the ground truth on these, I took as the reference partition just grouping people by year and gender, or just year. Can't remember which one, but kind of just a dumb partition. And mean curvature flow consistently did better than that, whereas Alan Kahn and the threshold dynamics were more mixed, and we're not sure why. So this points to maybe some kind of a stability issue where if you're fitting to the correct model, it will do the right thing, but there's some kind of noise in the real model that makes them not like a stochastic block model, and those methods are somewhat sensitive to that somehow. We're really not exactly sure why that happened. And then for the plumes example, the numbers are kind of the numbers are all negative because I made the reference putting all pixels in the same. But you still see that the mean curvature flow did the best out of all of them. But they all did significantly better than just no information at all. So that one we don't have as good a validation because the ground truth is truly inaccessible to us. And yeah, in terms of timing, the networks we were dealing with are only up to like 1 million edges or so, or a couple of 10 million edges maybe. And so the main take home should just be that the mean curvature flow was super duper fast and effective. Carnegie-Lin was of course slow, and Alan Kahn and MBO went in the middle. So the mean curvature flow was really effective, and it's kind of the dumbest thing that you could do once you've decided that this is a mean curvature flow problem. Evolve the equation, but it works really well. So yeah, anyways, there's a million directions you could take this. I think broadly this is part of the idea that maybe it is worth looking at networks from a mathematical and geometric point of view, and applying PDE techniques. There are many more out there. People have been doing conductance problems lately via these same techniques and balanced cuts and so forth. And so there's kind of a movement to see how well these tested PDE techniques will work in a new setting. The results so far, I think, have basically been positive. I think the other positive aspect of these results is that you can prove things like a convergence result when you send parameters to 0. You can prove descent conditions. You can expect stability in certain senses because we know how to solve PDEs stably. But as we saw from the Facebook example, there are other kinds of stability out there that we still need to understand. And yeah, and I think I've been talking with people in image processing who want to do this with multimodal analysis because they don't know how to tie the images produced by different modalities together appropriately. But the network scientists have been thinking about this forever. So if you form the images into graphs, you can form a multiplex graph and just apply all that technology. So there are lots of directions you could go. Come on, we can do this. Okay, well, it's not going to advance. That's the last slide, fortunately. So thank you for listening. I'm happy to talk about this more and take more questions.
There is one thing that I missed, the evaluation that you can try. Yeah, this slide.
Oh, this one?
The next one. So you mentioned that the third model is the one that essentially you made up where you have multi-scale community structure, right? Multi-resolution, right? So the 10, 20, 30, 40, 80, 160.
That's right.
Nodes, and then you have a click. Each of these is a click, or
no, but it's densely connected.
Densely connected.
It's I think we just did Erdős-Rényi with like a 20% connection probability or something.
So
or no, expected degree 20. Sorry, that's very different. Expected degree 20.
Expected degree 20, except for the first community
where we made it a click.
So that's a click. So my question is the following. So the resolution limit in modularity maximization says that you wouldn't be able to resolve any community whose the square root of the number of edges of the network, right?
Yes.
So this network has up to 5,120 nodes.
Yes.
So total size is going to be probably around 10,000.
Yeah, something like that. Yeah, it's 16,000. I think it came out to. Anyway, 10,000 or so. Yeah.
10,000 nodes. So average degree 20. So that would be 200,000 edges.
Yes. Mm-hmm.
So you wouldn't be able to resolve communities with sizes less than square root of 200,000, right?
Not with modularity.
Right.
And that's why with the stochastic block model, it's more able to get the multi.
Right, but then, I mean, you would still be able to resolve most of this community.
Yeah,
Not
it's
the
a
least
fine
models.
tail.
Right,
that
so
would
why
fail.
do you get 0?
0 in this case means perfect, right? Should I explain the metric again?
So okay, so 0 means perfect, so it means that you can get all the ones below square root of 200,000 as well.
Yes.
Okay.
Yeah, and actually, we it turns out we pushed very close to, because stochastic block model also has a kind of resolution limit, and we pushed very close to it because sometimes it would find, sometimes I think basically depending on the random generation of the graph, merging the last two together would result in a better objective. So I think we were right on the edge of the resolution limit of the stochastic block.
Do you have any sense of how this problem does with the detectability threshold?
People have asked me that, and I don't know the answer. I mean, it is a stochastic block model solver, so it will have exactly the same detectability threshold. The question is just whether the numerical solvers will succeed at getting there, and I don't know the answer yet.
So does anybody else have a question for us? So you mentioned that there's a work that's mapping like graph conductance problems to this PDE version.
Mhm.
So but there's so many methods now to solve even in the computer science community, general network science community. So what would be the advantage of doing it with the PDE approach?
Well, so for conductance, I actually don't know specifically because that's a problem that I'm not too familiar with.
Well, let me give you a hint or something maybe. How
Please,
it relates.
yes.
So a lot of the like fast methods or faster methods with graph conductance, they're actually doing some approximate version of solutions. So do
Okay.
the PDEs, do they give you approximate, like relaxed, or do they give you the exact problem, the solution to the exact problem?
I think. Well, I mean, it depends on how you do it, right? For the graph cut, like I said, I think it's basically outside of my knowledge for conductance because I haven't read that paper in a long time. But I mean, they are solving the actual nonlinear in the sense, but there are barriers like NP hardness that I think so far have made it impossible to prove that you're going to get the right answer, except in simple cases where you can actually go through things like the co-area theorem and prove that you'll get the right. Especially the one that was most successful is the semi-supervised graph cut, where you can prove that you'll get the right answer. In the other cases, I think that there's limits to what you can. So I don't know. I mean, more broadly in terms of what's the advantage of this, I think we're still trying to figure out exactly when it's going to be better and when it's going to be worse. I think what I've seen in my own work, because I've done more extensive comparisons than I shared today, is you kind of get these kind of principled PDE solvers versus at the largest scale for modularity, what you're going to use is something like a Louvain solver that's kind of a very fancy greedy approach, And so the question that I think should be resolved basically is, sure, the greedy approach is probably always going to be a little bit faster if speed is what really drives you. But the question is understanding the failure modes and whether a principled approach is going to have fewer failures and things like that. Because like in the network science Louvain method, it works okay, but it's been shown to be worse than other things that don't work at as high a scale. So what I really want to do over the summer, if the plans I'm scheming work out, is go to one of the DOE national labs, use their giant computers, and actually see to what extent you can plug in a production PDE solver and just instead of passing it a finite element grid, pass it a graph and see if it. So I think the answer is we don't know yet. Go ahead.
Did curvature also degree corrected the stochastic block model?
I didn't say this. What I showed you is all degree corrected. Although I've done the math for non-degree corrected and it works for that. So this is degree corrected.
So because there is a paper recently by Newman, he showed that degree corrected the stochastic block model is equivalent modularity for partition planted model.
Yes.
So have you seen any kind of equivalence between these?
Yeah, I mean the paper by Newman was actually what gave us the idea to look at the stochastic block model, because we had already solved modularity as a total variation problem. We thought, oh well, is SBM just also a total variation problem? And it turns out the answer is yes, but that's the surface tension is a more elegant way to express what's going on. Yeah, I've read the Newman paper carefully. It's a good one.
There's no other questions. Let's thank Zach again. feel looking back.
Yeah, I mean, oh yeah, I'm not doing the recording.
So it's not through. Oh, this is the
This
computer
is
you're
just my
using.
machine. Yeah.
Oh, this is your.
I think the console over there is doing the recording, maybe. Yeah, I mean, it's kind of weird because, you know, when you're actually doing the work, you're always in this sea of weeds and details. And then when you present to someone, you just like this very broad picture that you kind of thought was true months ago and took 2 months to validate.
And I remember hearing like Eve talking about the stuff which was like, you know, years ago, and like it makes more sense to me.
Yeah, well, I'm glad it was helpful. I don't know the computer science crowd as well, so I was hoping that this would connect.